Okay, so let's discuss another question. Okay, so from theory of machine, here it is written that you have a cantilever beam with negligible mass and with uniform flexural rigidity. So here it's a cantilever beam. The mass is neglected, but it has some stiffness. That's why there's a question about flexural rigidity. So flexural rigidity is EI. EI is basically the flexural rigidity. And the length is given, the entire length is given as 0.01 meter. The frequency of vibration with 1 kg mass attached is 100 Hz. So frequency of vibration is 100 Hz. And what is the rigidity value? So basically, what is the EI value? This is actually another way of getting the flexural rigidity by this. Okay, so what we have to do is the cantilever beam basically acts just like a spring. Now when you place a mass here, it deflects, and the deflection profile looks like this. So this is deflection. Okay, so it's something like you have a spring and you keep a mass, so there is a static deflection. So this delta is static deflection. Okay, and now if you just perturb it and leave it from this undeformed position, it's going to exhibit simple harmonic motion, because you have inertia as well as you have restoring forces in the system. The restoring forces being the stiffness of the beam, as well as the inertia being the mass and because of the mass. So, and there are no damping effects, so it is going to exhibit a simple harmonic motion. Now, so this is something like, so how do you get this delta? So understand that when you have a spring and you have a mass m, okay, so, and the static deflection is delta. So how do you write? I mean, the mg is k delta, and what is your natural frequency? Natural frequency is root k by m. Okay, and root k by m is nothing but g by delta, where delta is static deflection. So if you can convert your problem into a spring mass system, then one of the way of finding natural frequency is, if you know the static deflection, okay, root g by static deflection, or root over g by static deflection is another way of getting natural frequency. So now how do you know now? So this is similar to here. The cantilever problem we can model as a spring and a mass system, where delta is a static deflection. So how do you get this delta? We get it from deflection of beams, where if you have a end load at the cantilever and the end load is P, then what is the deflection? The deflection is given as, if you use those double integration method, you will get that the deflection when you have a end load at the end of a cantilever is PL cube by 3EI. So P is mg here, okay, the weight of the mass, into L cube by 3EI. And what we need is basically g by delta to calculate the natural frequency. So g by delta is 3EI by mL cube, right? Okay, so let's convert that, and omega is given as 2 pi f is your natural frequency, okay, into g by delta is basically 3EI by mL cube. So let's substitute 2 pi f is 100 Hz, and 3 EI is something which we need to calculate, flexural rigidity. M is 1 kg, yeah, M is 1 kg, and L is 0.1, so 0.01 whole cube. So from this, if we just square it and calculate EI, we get about 0.13. EI is about 0.13, and the units would be, well, E units is Newton per mm, Newton per mm square, Newton per meter square actually, E units, and I will be kg meter square. So this is Newton kg meter power 4 is mass moment of inertia, mr square, right? Mr square. Yeah, mass moment of inertia, but remember that this is not mass moment of inertia, this is area moment of inertia, so it's m power 4. Yeah, So Newton meter square is your units. Remember, that's area moment of inertia, because in the beams when you have the cross section is what is dictated by I. So it's 0.13 roughly. 0.13 is the answer. Thank you.